Either be scouring or it will not cause deposition of the sediment in the bed. So that was the principle, and by that principle we could do design of alluvial channel. and that particular velocity we termed as critical velocity. And then, but these two theories or the equations derived or equation used in these two theories are empirical, I mean based on some observation, and that way it has some drawbacks. And again in the entire procedure there are some drawbacks. Those drawbacks also we discussed in the last class. And then as these are empirical, so people were trying to develop some analytical basis for designing alluvial channel. And then USBR, United States Bureau of Reclamation, so they started working on one method called tractive force method. We started in the last class what the tractive force method is, and we will be continuing with that tractive force method. And say first in the last class we did define what is, say, tractive force. So it is the force exerted by the flowing water on the perimeter of the channel, or say on the material of the sides and bed. So the in suppose uniform flow condition, if we talk about, then weight of the fluid in the direction of the flow is actually the tractive force, and that we try to equate with the resistance force to find what is the critical tractive force and all. Well, then we were talking about unit tractive force. That means this tractive force per unit area. Well, that we refer as unit tractive force, also called as a drag force or shear force. So these different nomenclature are used. And then we were discussing in the last class about distribution of tractive force. Means, say, we could see that unit tractive force. That unit tractive force means that was coming, in fact, as average unit tractive force, because the force exerted by the fluid we were considering on the entire surface, the surface which is in contact with the water during that length of the channel. And then we divided it by the entire surface length which is in contact with the fluid motion, which is in contact with the fluid. Here our fluid is water, of course, we are talking about. And so that way the stress what we are getting, tractive force, that per unit area is in fact a on average basis. So average tractive force. But in reality, the tractive force exerted by the fluid on the side of the canal will not be uniform all over the surface. It will be more maybe at the bottom at certain point, at the center point it may be more. Then if it is a trapezoidal channel, then on the side towards the top the tractive force will be less, but towards the bottom on the side that will be more. So that way tractive force distribution we were talking about, and we did draw a diagram for trapezoidal channel where we could just draw a trapezoidal channel, and we were showing how the tractive force distribution can be plotted on the side and on the bed of the channel. Well, but that distribution we draw like this just to recall, because from here we will be moving ahead again. So that suppose it is a trapezoidal channel, of course we were considering a channel where our y, that is the depth y, is say 1/4 of the bed, or we can say that bed width is 4y of the depth, well 4 times the depth. In that case we got that tractive force distribution. Of course pattern will be same, it is like that, and here it is almost uniformly distributed, it is almost uniformly distributed, and here again it will be like that, here it's more. So maximum tractive force we could get at this point. And so this maximum tractive force, and if we just compare the maximum tractive force, if we compare the maximum tractive force at the bed and at the side, we can see that at the bed it is more, and this can be expressed in terms of W, Y and S. It is the unit, this W is unit weight of water. So this unit weight of water, then the depth, then the bed slope. Okay, so based on that we could derive the expression, but there will be a term say 0.77, that means it is not exactly equal to WYS, but it will be a percentage of WYS, this will be, and maximum can be WYS, that I will show just in the next slide. But this can be say 0.77, 0.8, something like that. This can be, and so that factor we can write say x into WYX, where x can be say 0.7, 0.8, like that, 0.6, anything it can be, and that way this can have different value. Well, then similarly y also can be, similarly in the side tractive force also this can be expressed as WY and S, and similarly here also a product will be coming, so x into that I am writing here. And now this was given for this particular channel where width of the channel is 4 times the depth of the channel, and we did discuss what the value of x there, and then this slope, okay, my diagram is not proper, but the slope is, say if it is 1, this is 1.5 for that sort of side slope. If it is 1, this is 1.5, and for that sort of side slope and for this shape where b is equal to 4y, for that we gave some value of x in the last class, and that we were discussing how shear stress, or rather we will call it as how unit tractive force get distributed, tractive stress get distributed on the side. Well, now say in reality we'll be having different type of channel. Say B by Y ratio. Here our B by Y ratio is 4. B by Y, if we make it, is 4. But always the B by Y will not be 4. And here our side slope is equal to 1:1.5:1. But this will not be always same. So if the side slope changes, say 1:2, like that, if it is changes Z value, then and the B by Y ratio changes, then how this will vary, how this maximum tractive shear stress or unit shear force varies, so that we need to know. And USBR, United States Bureau of Reclamation, again gave some curve for that. Which curve can be, these curves can be used for design of tractive force. Let us see how these curves are. Well, first you can see this is here in this graph. On this side it is B by Y ratio is plotted on this side. So B by Y ratio they examine, say up to 10 we can have, and then on this side, that is on the y-axis, it is unit tractive force in terms of WYS. W means again unit weight of water. So suppose if I get a point here, 0.4 means it is 0.4 WYS. Okay, let me draw the curve, and then it is actually a family of curve. It is not a single curve, it is family of curve which were drawn for different side slope. Well, and for even for rectangular channel, and for rectangular channel if I draw for the side, and this unit tractive force is for side tractive force we are talking about, that is in a channel it is at the side. So for rectangular channel it is like this, that is from 0 it is starting, and it is going like this, and then it is going like this. It is a smooth curve, of course, it is going like this. So this sort of curve were obtained for rectangular channel. Well, I must say that my curve may not be exactly like the curve that was given, but just I am trying to show what the trend is. And so this is for rectangular. And then for trapezoidal, again, say it will be starting from about a little higher from 0.5, and then it is going like this, that it will be going like this. Okay, this curve is going like this. My space is less, painted is little larger, but still let me try. And then so this curve is for say Z equal to 1.5. 5. And then this is rectangular. This is rectangular. And of course, if we draw for a for a point say z equal to 1, it will be almost following the same line, but it will be starting from here. It will be starting from here. So this we can say it is z equal to 1. And then if z increases to 2, if z increases to 2, the curve start little higher, and then it will be, but maximum limit is always remaining within 0.7 and 8, so it is going like that. This is for z equal to 2. Well, so that way a family of curves was given. Curve was given by USBR, and following that we can just try our design, and that is quite helpful. Say we initially, if we take that our b by y ratio is 3, then from that point, if we consider that b by y ratio is 3, then what will be, and if we consider that it will be a rectangular channel, then we can see what is the side attractive stress, that is. Of course, after that we'll need to check whether that channel will be sufficient for carrying the required discharge. Okay, that will be coming later. And then for again the unit bed tractive stress, unit bed tractive force, say this is we can plot that as given by USBR when it is bed. Then for rectangular, this will be starting from here, and this will be like this. This is going up to almost 1. It is going up to almost 1 like that. And if I extend it, it will be going up to 1. Then say for trapezoidal, it was interesting to observe, because it is bed, although it is trapezoidal, but say side slope, whether it is more or less, it doesn't influence that much. But still, for the z equal to 2 and 1.5, we are drawing for bed, so it starts from say very close to 3, but it follows almost that one. Then from 5 onward, it just leave this axis, and then it goes like that. And for higher value of, in fact, it will be passing more steeper like this. And for higher value of b by y ratio, it goes almost up to this point 1, almost up to 1. Okay. So what we can see, that for a b by y ratio of say 8, 9 or around that, this tractive force is becoming equal to WYS, that is, which we could get for wide rectangular channel, and just equating that our component of gravity force acting in the direction of flow, and that when we put as our tractive force tau, and then when we divide it by the contact area, then we get the tractive force per unit area. That symbol here itself we call as tau, and that value we got that it is equal to W, R and S, where R is the hydraulic radius. And for wide rectangular channel, we got it that R is approximately equal to Y, and that's why we can consider this as WYS. And as our B by Y ratio is increasing, means we are talking about a wide rectangular channel, and B is larger as compared to Y. That's why B by Y ratio is quite larger. And as it is increasing, we are finding that it is becoming, this fraction or the product factor is becoming almost equal to 1. And what we could derive theoretically is valid here. So these are the curves that were provided by USBR. Now, that another point is more important here, that say we are using these curves, and now one curve is giving us the tractive force for the side, and these curves are giving for tractive force for the side, and these curves are giving tractive force for the bed. That is the tractive force exerted, we can say like this, tractive force exerted by the fluid on the channel. This is what we are talking about. And for design purpose, we should know again how much is the resistance of this tractive force. And then there is a question that can we have some relationship between tractive force at side and tractive force at bed? Can we have some relation between these two, so that when we will try to find a permissible tractive stress, then for some of our analysis we may get that okay, tractive force at bed is equal to this much, permissible tractive force. Permissible, to be more precise, we can say permissible unit tractive force at the bed is this much. Now, if we design it from that consideration, that may not be safe, because on the side it may not be safe. So we need to know what is the permissible tractive shear stress unit tractive shear force at the side. So now that if we could derive by having a relationship between tractive force at bed and tractive force at side, then it would have been much better. So, and that can be derived very easily from our conceptual understanding of the geometry of the channel and just the equating the forces, we can do that. And let us see. So to just see that, let us take a channel. Well, let us consider one channel. Say this is our channel and the water is flowing in this channel. And then when water will be flowing, let me just show that suppose this is the water level and it is flowing. Okay, I'm not drawing it because something else I'll have to draw, but well, for just to appreciate that, okay, say water level is there, you just imagine that we have water level at this level. We can draw a line to show, okay, just very small drops. Okay, so this is what the water level, okay, I can draw it here. Say here the water level, and then the water is flowing. So, well, that will not create any problem. So that way water is flowing with a particular depth. And then in this channel, here is our, say, side of the channel. We are digging it, and then this way, after digging it, it is we are making the channel. Now let us see that, say, side slope of this channel is suppose theta. It is supposed theta. Well, just to analyze, let us consider, say we have a small area. Let us consider a small area, say A. Let us consider a small area A. And then when water is flowing in this direction, okay, then the tractive force exerted on this area, say area is A, and let the tractive force exerted on this area is, say, tau S. That is, tractive force means we are always we are meaning by unit tractive force means tractive stress. So tractive stress exerted by the fluid on this particle is, say, tau S. Then if we say that this area is A, this small area, then the tractive force on this area will be, on this particular area will be tau S into A. This area will be tau S into A. Fine. Now let us see whether this area or that area, if we talk about a very small portion, then it may ultimately come down to a sediment particle even. Now, whether this is getting subjected to some other forces also. Well, the weight of this particle is acting vertically downward. Weight of this particle will be acting vertically downward. If I draw the same area here, then it is convenient to show that it will be acting vertically downward. Say this is also area A, and this weight of this will be acting vertically downward. And let me write that weight as, say, W dash. This is, I am not writing unit weight, I am writing the complete weight of the sediment of that particular portion A. And that, why I am writing W dash? Because this is underwater. We are considering the force exerted, tractive force exerted means this is under water. It will be submerged by the water. So weight of the particle will be basically submerged weight, and that's why we are writing this as W dash. Well, so this W dash is the weight, and then this particle or particles or the area itself will be having a tendency to slide down along the slope. Or rather we can say that there is another force which is acting in this direction, and because of which, because our interest is to know that what are the forces acting to move this particle from its location, move these particles from its location, rather. Okay, so one is the tractive stress, and now we are talking is a tractive force, which is tau s into A. Another is the force that is trying to move it along the slope in the downward direction because of the gravity. And that gravity is basically this weight of the particle, and then what that angle is, we know that this angle is theta. So between this line and that line, so if I draw this line and if I draw a normal to this particular slope, then this angle will be theta. So the angle just acting in this direction will be, say, force acting in this direction will be W sine theta. Theta is away from this part. So this is theta. So, and theta is the angle between this line and that line. Okay, and this line is perpendicular to this plane, means this line, and then it is perpendicular to this. So this is theta, and this is or W sine theta. W sine theta. Okay, that particular force we can write W sine theta, and here I am writing this as W sine theta. These two forces are acting. W dash, well, we are writing W dash. So what are the net forces that is acting on this particular area to disturb this sediment? Well, there are some other forces which will try to resist this motion. But now we are talking about, or we are looking into the forces which are trying to disturb this, particles. So these two forces, that is W dash sine theta and this tau s A, are the forces that is trying to disturb the particle from its position. And then what is the resultant of that? We can draw the resultant of that just by completing this and then joining this. So this is what the resultant. And that resultant, if I write as F1, say, disturbing force. So that how we can write? This will be d square, tau s into a tau s square a square plus W dash square sine square theta, and then taking root of that we will be getting this force. So you can write the force disturbing, or we can write the disturbing force. The disturbing force. Well, the disturbing force F1 is equal to root over, say, tau s square